exterior angle of a regular polygon measures 166 2/3 degrees. How many sides does it have? So that's the interior, 166 2/3. To get the exterior, I subtract from 180 and I get 13 1/3. All right, so that means each exterior angle measures 13 1/3 degrees, and they're all the same. So to figure out how many angles there are, the exteriors always add up to 360. I divide 360 by 13 1/3. That becomes 360 divided by 40/3. When I divide fractions, I multiply by the reciprocal. When I cross cancel, that becomes 9. And 9 times 3 is 26. All right? So if they give you the interior angle measure of the polygon, my suggestion is subtract from 180 to get the exterior angle, and then basically divide that into 360 to get the total number.
How did you do the like, why is it 40 over, is it because, wait, I think I did that.
From a mixed number and an improper fraction.
Okay, yeah.
So that's for the benefit of people who don't have calculators. If they have to do it out loud. All right. Everybody else good? All right, let's take a look-see at some honors problems then. It says the ratio between the interior and exterior angle measures of a regular polygon is 3:2. How many sides does it have? So that's what we're looking at. We don't know what the common multiplier is, so that's going to be X. We do know they form a linear pair. So I take the two components, which are 3x and 2x, add them up and set it equal to 180. All right. Now, everybody good with that idea? The equation I set up. So now I'm going to solve it. 3x plus 2x is 5x. Divide by 5 and you get 36. That's what we consider our common multiplier, so we can plug that back in. 3 times 36 is 108. 2 times 36 is 72. So that tells us the interior angle measure is 108, and the exterior angles measure is 72. Okay, now we don't know what the interiors add up to, but we know what the exteriors add up to, 360. I take that 360 and divide it by the individual angle measure, which is 72. 360 divided by 72 is 5. That tells me, ladies and gentlemen, that that figure is a pentagon. So if they give you a ratio between the interior and exteriors, you give it any variable you want, make the ratio of the coefficients, add them up, set it equal to 180, and then solve from there.
I have a question. When you divide by the exterior angle, like 360 divided by the exterior angle, is it always going to be a whole number?
Has to be, otherwise it isn't. Otherwise it doesn't exist.
All right, thank you.
Yeah, it's okay. So if you get a fraction or decimal when you do this, something went wrong along the way.
Okay.
Right? Okay. Next up, give it an equal angular polygon with the following information. The interior angle is 4x squared minus 300 minus 100. The exterior angle is 3x. All right, so once again, the interior and the exterior, no matter what relationship they give us, is always going to be supplementary. All right, so 4x squared minus 100 plus 3x is equal to 180. I'm going to get it in standard form. 4x squared plus 3x minus 280 equals 0. Okay. Everybody good? Okay. Well, now you're going to have to factor. And now you're going to have to factor. And that factors into whatever method you use. 4x plus 35, x minus 8. All right, so that's what it factors into, whether you use substitute, whether you use guess and check, grouping, all right, or slide and divide. That's what it factors into. 4x plus 35, x minus 8. Now, 4x plus 35 gives me a solution of negative 35 over 4. If I plug that back in, I'm multiplying a negative times a positive, it's still going to be negative. For this class, we can't have any negative angles, so that is extraneous. The opposite of negative 8 would be 8, so 8 is my only actual solution. I then plug it in. Personally, I'm only going to plug it into the exterior, and you'll see why. 3 times 8 is 24. And we know the exteriors add up to 360, and we know each one measures 24. So to get the number of sides, I can just do 360 divided by 24, and my answer is 15. So that, ladies and gentlemen, is a 15. All right. So you may have a quadratic application somewhere along the line. Everybody good? Okay. All right. The diagram at right shows a section of a semi-regular tessellation, which is created by taking the same pattern of regular polygons and arranging them so that there are no gaps between the polygons. If point B is a vertex where all the different regular polygons meet, what is the remaining shape that was removed? In other words, what shape would be needed to add would need to be added at B, fit the regular polygons together so that there is no gap. All right, so here's the idea. It's like a jigsaw puzzle. Everything has to fit perfectly. All right, and for that to occur, all those angles would have to add up to 360. Everybody good with that idea? All right. So I have a square. They're telling me they're all regular polygons, so that measures 90 degrees. I have another square, so I know that that's also 90 degrees. I have an equilateral triangle in between. Equilateral triangles, we know from earlier in the year, are also equal angular. So 180 divided by 3 means that angle is 60 degrees. So I already have a 90 degree angle, 90 degree angle, and a 60 degree angle. 90 and 90 is 180. 180 and 60 is 240 degrees. So the angles showing are 240 degrees. Figure out what's missing. Obviously, I'm going to find the difference, which means I subtract 360 the whole way around minus the 240 I know is there, which is 120 degrees. That means that angle, the angle of B, is 120 degrees. All right. So again, if I'm looking at this in terms of interiors and exteriors, there's the 120. The exterior then is 60 degrees. Exteriors add up to 360. 360 divided by 60 is 6. Ladies and gentlemen, I have a 6-sided figure, and most of us call that a hexagon. All right. Everybody good? All right, last one then. The exterior angle measure of a regular octagon is given by the expression 10x plus 3y. The exterior angle measure of a regular nonagon would be 5x plus 5y. The exterior angle measure of a regular n-gon is x plus 3y. Find that. Okay. Well, first off, let's add what we know. An octagon has 8 sides. We're talking about the exterior angle, so we're going to do 360 divided by 8, and that's 45. So that means that 10x plus 3y is equivalent to 45 degrees. Exterior angle measure of a regular nonagon. A nonagon has 9 sides. I'm going to do 360 divided by 9. That gives me 40 degrees, which means the exterior angle measure of a regular nonagon is 40 degrees. All right, ladies and gentlemen, I have 2 equations with 2 variables. I have myself a system. You can solve it using substitution or elimination. Because 5 goes into 10 evenly, I'm going to use elimination. Top equation is going to stay exactly the same. Nx plus 3y is 45. The bottom equation I'm going to multiply by -2. The result would be negative 10x minus 10y equals -80. When I add straight down, 10x minus 10x is going to cancel out. 3 minus 10 is -7y. I get -35. How do I get rid of a multiplication by -7? You divide by -7. And y equals +5. I'm then going to take that and plug it into either one of these equations. If I plug it into the bottom one, 5x plus, if y is 5, 5 times 5 is 25, and set that equal to 40. Subtract 25, divide by 5, and x comes out to be 3. Why that's important? Because we're trying to figure out n. I plug them both back in, so now this becomes 3 plus 3 times 5. 3 times 5 is 15. 15 plus 3 is 18. So that means the exterior angle measure of our polygon we're trying to find is 18. Well, we take the 360 that we know they add up to, divide by the 18, which one measures, and 360 divided by 18 means I have myself a 20. And thus you have a systems application. Everybody good? Okay, so your homework tonight, 6-1 practice. Okay? For 1 through 24, you really don't need to show work, you're just plugging in. All right? 25, 26, 28, and 29 are the ones you're showing work for. All right? Because those are the ones solving equations. 27, you don't really need to show work if you don't want to. All right? So 25, 26, 28, 29 need to see work. All right? 30 through 35, again, I don't really need to see any work. Same thing with 36 to 44 and moving your way down. It's a lot, but they should be able to be done quickly. That's the point of it. There isn't really a lot of work to be shown. All right, and that is what is due tonight at midnight. All right, so our next lesson involves 6-2 and 6-3. And that, my friends, is properties of parallelograms. Okay? So we're going to be dealing with quadrilaterals from this point moving forward for a few weeks. We'll start with parallelograms, then next week we'll start special parallelograms, and then we'll end it up with kites and trapezoids as we go into the third marking period. All right, our goals include to use relationships among sides and angles of parallelograms, to use relationships among the diagonals of parallelograms, and then finally to determine if a quadrilateral is a parallelogram. Basically, 6-2 outlines the properties. 6-3 is going to be, for the most part, the converse of that. All right? So, we start with a definition of a parallelogram. Parallelogram. I'm good. A parallelogram is, are you looking for something? I'm good. I got to go still teach for 11 more minutes. So not all of us have a period off. All right?
Want to go in or no? I'll wait for you.
Nah.
Sure?
I'm good. No, I'm good. I got to get some work done. Thank you, though. A parallelogram is a quadrilateral whose opposite sides are parallel. Whose opposite sides are parallel. Parallelogram is a quadrilateral whose opposite sides are parallel. So whenever you mention the definition of a parallelogram, that's it. All right, there's going to be other properties that I'm sure all of you know already. All right, because they're pretty straightforward. We're going to justify them. But when you're asked to give the definition of a parallelogram, it's a quadrilateral whose opposite sides are parallel. Now, what we then do is we draw on a diagonal. It's not going to matter which. Okay, but here's the idea. All right, before we get into that, as people are jotting down those, all right, recall that if I extend the sides, all right, and I make that a transversal, A and B are same side interior angles. All right, and as you recall from chapter 3, those are supplementary. All right, so in looking at this parallelogram, all right, in looking at this parallelogram, A and B are what we call consecutive vertices or consecutive angles because they share a side. A and C are opposite angles. They're opposite angles. They do not share a side. All right, everybody good with the difference between the two? So A and B are are connected. A and C are not. All right. Now, because of what we pinpointed up here, the same side interiors, all right, consecutive angles of a parallelogram are always going to be supplementary. Are always going to be supplementary. So if they tell you what angle D is, you subtract from 180 to get what A is. All right. So basically, we'll start this proof with this statement. ABCD is a parallelogram. All right, ABCD is a parallelogram. Okay. Well, just like any proof, we start with what that tells us, and that's the definition. So we say AB is parallel to CD, and AD is parallel to BC. So the first one's given, second one is definition of a parallelogram. And that's the symbol if you want to use it for parallelogram. All right, well, if we look at these as parallel lines and we look at BD as a transversal, 1 and 2 are alternate interior angles. If we look at AD and BC as parallel lines, and we look at BD as a transversal, then 3 and 4 are alternate interior angles. And as we know from earlier in the year, when lines are parallel, alternate interior angles are going to be congruent. So that allows me to say angle 1 congruent to angle 2, and angle 3 congruent to angle 4. AIA. Alternate interior angle. Hopefully it's been ingrained in your head by now that as soon as you have a diagonal drawn in this case, that is going to be a shared side, and that, ladies and gentlemen, is BD. So we're going to say BD is congruent to BD. All right, by the reflexive property. BD is congruent to BD by the reflexive property. All right. Well, angle 1 is congruent to angle 2. Angle 3 is congruent to angle 4. I got 2 angles of one triangle congruent to 2 angles of another, along with a side, and that's the included side. So, ladies and gentlemen, I have myself angle, side angle. All right, I just got to make sure I name them in the right way to take advantage of my properties. The triangle ABD is congruent to triangle. So ABD goes nothing, 1, 2. So following the same order down below, nothing, 1, 2 gives me CDB. The triangle ABD is congruent to triangle CDB. Okay? As always, what follows our statement, triangle congruency is CPCTC. And this is where our properties are going to kick in. Angle A, which is the first letter here, is going to be congruent to angle C, the first letter there. All right. Notice A and C were opposite angles. All right. As a result, we are going to say that opposite angles of a parallelogram are always congruent. All right. In addition to that, AB, the first 2 letters are congruent to CD for the same reason, CPCTC. Well, AB and CD, all right, do not share a vertex. AB and CD are considered opposite sides. They don't share an endpoint. And through CPCTC, we just realized that those opposite sides are always going to be. All right, so tomorrow when you come back, we'll go through, we'll put all that together. on the chart on the next page so you have everything together, and then we'll go through the one remaining property using a different proof. So if you are good to go, I am good to go. Stay safe. Don't forget 6.1 practice due tonight. Bye,
Have a
guys.
good day. Bye.
Hi, Mr. Strada.
Bye,
Have a
guys.
good day.
Yeah, I know.
I have one question.
Yes.
Oh, wow, this is sweet as hell.
Just to like clarify, when you divide 360 by like the exterior, you get the number of sides.
Yep.
And then when you divide 360 by the number of sides, you get the exterior.
Get the actual angle measure.
Oh, you get the actual angle measure.
Yes. So that may come out to be a fraction.
Oh, okay.
You know what I
Thank
mean?
you.
The angle measure can be a fraction, but the number of sides can't.
All right. Thank you.
All right. Mary Bear, what are you doing?
Strada!
What are you doing?
I missed you, so I came on Angela's Zoom call.
I see that. Everything good?
He's eating. How are you?
Good. How's pre-calc? Good?
It's okay.
Eh,
Yeah, no, I like Mr. Haggerty. He makes it pretty easy, but
yeah.
it's not that bad.
Yeah. So,
All right, I'll let you go. I just want to say hello.
all
Miss
right.
you, Strada.
I'll see you next week, hopefully, if you come back.
Yeah.
Yeah.